Welcome all. In this lecture, we are dealing with the analysis of the multiple degree of freedom system subjected to blast loading. In the last lecture, we took up a case of a multi-story building. We modeled the multi-story building using the lumped mass approach, and using the lumped mass approach, we calculated the stiffness of the system, we calculated the mass of the system, and we calculated the mode shifts and frequency of the system. And using the mode shift frequency of the system, we calculated the time period, and using the design charts, we evaluated the response of the system, and the response of the system was within the limits. So, we will continue the example. Okay. So, after checking for the maximum deformation limits, okay, we will check the deflection of members in the rigid frame. Okay. In the first step, we check the overall response of the system. Now, we will check for the individual members. Okay. So, first we take the exterior beam. Okay. For an elastic plastic response, okay, we take the average load mass factor for the plastic and elastic response. Okay. The meaning of this term is that we are assuming that the system is neither in the elastic range or neither in the fully plastic range. Okay. It is somewhere in between. Okay. And this inference of the elastoplastic response, okay, comes from the limitation for the allowable deformation and the rotations. Okay. So, this limits, okay, will give us an idea of where our structure is. Okay. So, in the particular problem, okay, we saw that this requirement, okay, is stringent than the requirement for the personal protection. Okay. So, it means that the system has not reached in the pure plastic region. Okay. It is somewhere in between the elastic and the plastic region. So, this is the elastoplastic region. Our system is in the elastoplastic region. Okay. So, getting that inference, okay, we are using the ratios for the elastoplastic response. Okay. So, KLM, the load mass factor, we are taking the average from the elastoplastic response. Okay. So, we calculated the equivalent mass and we calculated the equivalent stiffness. Okay. We calculated the time period. Okay. So, this is the time period for the beam. Okay. And using the design chart, okay, again we calculate the deflection in the beam. Okay. And using the deflection in the beam, we calculated the rotation in the beam. Okay. So, the rotation is 0.16 degrees, okay, which is less than 1 degree. Okay. So, this configuration is okay. Okay. The rotations are under the prescribed limits as well as the allowable sway in the system. Okay. So, we compared for the allowable sway in the system as well as we compared for the allowable rotation in the systems, and both are within the limits. Okay. After that, we take the exterior column. Okay. So, for the exterior column, earlier we have taken the exterior beam. Okay. So, what we are doing is that we are checking the each of the members. Okay. So, first we had a check for the exterior beams, the rotation was within limits. After that, we are taking the exterior column. Okay. So, for the exterior column also, we are taking the average load mass factor, okay, assuming an elastoplastic response. We are calculating the equivalent mass, we are calculating the equivalent stiffness, okay, and then we are calculating the time period of the system, and again using the design chart, we are calculating the maximum deflection in the system, and using the maximum deflection in the system, we are calculating the rotation in the exterior column, which is again under the prescribed limits. So, the system configuration is okay. Okay. So, the assumed values are okay. Okay. After that, the local mechanism of the deflections meet the criteria. Okay. The side sway deflection is permissible, the assumed sections are suitable for analysis. Okay. After that, what we do is that now here the problem ends. Okay. So, our local mechanisms were meeting the criteria, our beam was meeting the our column was meeting the criteria, and our beam was meeting the criteria. Okay. So, the local mechanisms were meeting the criteria as well as the side sway of the system is within the limits. Okay. So, the entire configuration that we have assumed, okay, the entire configuration that we have assumed meets the permissible criteria, and this design can be used for the structure. Okay. What we can also do is that if we look here, if we look closely at the values, the allowable deformation is 418 millimeters. Okay. Our section is only deforming 32 millimeters. Okay. So, what we can do is that we can again go for the optimization of the sections. Okay. So, the assumed sections are, so whatever we have assumed the sections, okay, they are okay, but again we can use a smaller size also. Okay. If you want to achieve the economy, okay, we can again go for the optimization process also, because we have a lot of margin here. Similarly, if you look into the rotation mechanism, okay, allowable is 1 degree, it is coming out to be only 0.16 degrees. Okay. Again in the column mechanism also allowable is 1 degree, it is coming out to be 0.47 degrees. So, there is a lot of margin. Okay. So, what we can do is that we can again try to optimize our section also, so that we can achieve economy in our design. Okay. Otherwise, from the entire design perspective or from the academic point of view, these sections will resist the given blast load and it will perform as per the design criteria. Okay. So, moving ahead. Okay. So, now what we can do is that we can look into the controlled progressive collapse also. Okay. So, what we are trying to do is that we can achieve a progressive collapse mechanism in our system also. Okay. So, what we can do is that we can make a number, okay, that is called the DCR, demand capacity ratio. Okay. So, demand capacity ratio is used to evaluate the risk of progressive collapse in the structure. Okay. So, this is nothing but the ratio of the demand to the capacity. Okay. So, it compares the demand, the actual force in a member, to the capacity, that is the design strength. Okay. The force considered include the bending moment, the axial force, the shear force and the torsional moment. Okay. So, what we can do is that we can have a configuration, okay, of a structure, okay, and we can one by one remove the column. Okay. So, once we remove it, the moments will be, or the entire system will be redistributed. Okay. So, after redistribution we can check the demand to capacity ratio, the DCR ratio. A DCR ratio more than 1 indicates that the member is overstretched and may be at risk. Okay. So, using this philosophy, okay, we can evaluate the controlled progressive collapse mechanism in a given system. Okay. So, DCR is defined as the QUD, actual force in the structural member, that is the numerator, and QCE, ultimate unfactored capacity of the structural member. Okay. Remember, this is the unfactored capacity of the structural member, and DCR ratio means that the structure is overstressed as compared to its strength. Okay. So, it will have a high probability of failure. Okay. A DCR greater than 1 indicates the member is overstretched and may be at risk. A DCR greater than 2 indicates failure for conventional structural configuration. A DCR greater than 1.5 indicates failure for unusual structural configurations. Okay. So, conventional configurations refers to structure with simple or standard layouts. Okay. So, if demand to capacity ratio exceeds the allowed demand, the member must be strengthened. Okay. So, if DCR is greater than 1, there is a need to strengthen the member. So, in the proposed design analysis, okay, whatever we are doing, okay, we are always trying to keep the DCR less than 1, so that our members are not overstressed, or the actual forces coming to the member are less than the design capacity of the system. Okay. So, here this thing was evident in the analysis also. Okay. So, here the allowable capacity was 418, okay, but the actual thing is 32 only. It means that if we compare the forces in the system, okay, to the strength of the system, our DCR will be less than 1. Okay. So, in order to optimize the system, what we can do is that we can lessen the section capacity, okay, such that the DCR becomes close to 1. Okay. Okay. So, this way we can also achieve the optimization of a section. Okay. The peak loads are uncertain due to varying blast direction and location. Okay. So, there is a catch also. If we keep on optimizing to a very extreme limit such that our DCR is almost equal to 1, okay, we have to take into account that there is uncertainty in the loading also. Okay. So, depending upon the varying direction, locations, different mechanisms that we do not understand, okay, or some simplification in our analysis procedure, okay, it might happen that the DCR goes greater than 1, okay, in the realistic scenario. Okay. So, it is always advisable to keep DCR less than 1 and do not optimize till we reach the limit. Okay. So, we always have to keep a margin whenever we are designing a system. Okay. The UDQ, okay, ultimate unfactored demand value, is always less than or equal to the CQ capacity. Okay. So, the demand value should be kept less than the capacity value. Okay. So, there should always be a margin maintained, okay, so that due to the uncertainty in the loading or uncertainty in the interaction or for any other factor, the DCR value does not becomes equal to or more than once and the member becomes overstressed. Okay. So, this has to be maintained always. So, now we are showing the simulation of a beam, okay, a concrete beam using LS Dyna. So, what we are doing is that we are showing the step by step for the finite element analysis. Okay. So, in step 1, okay, this software, okay, the modeling part is freely available. Okay. You can freely download from the internet. Okay. So, the LS Dyna pre-post processor. Okay. So, we have used the LS Dyna pre-post processor to create the section of the beam. Okay. So, first of all, what we need to do is that we need to create the section. Okay. So, first of all, we need to choose the, we can do is that we can make this 4 coordinates, okay, and we can join the fold lines. Okay. And in the fold lines, after we join the fold lines, what we can do is that we can make the plate. Okay. And then what we can do is that we can extrude the plate in the vertical direction, okay, so that we have a solid member. Okay. And subsequently, here also what we can do is that we can mesh the plate. Okay. So, after meshing also we can extrude the plate such that we get a solid section. Okay. So, first of all, we need to create the geometry of the section. Okay. After we create the geometry of the section, we need to mesh the section. Okay. After meshing the system, okay, let us say we are trying to create a reinforced concrete beam. Okay. So, after that what we can do is that we can switch off the system. Okay. So, we can switch off the system. Okay. So, this is the concrete beam that we have created. Okay. So, after creating this thing, what we can do is that we can switch off the system and then we can create parallel lines like this. Okay. We have to create the nodes, and from the nodes we can join this lines. Okay. And this lines we can give the property, we can mesh it, okay, and give the properties of the beam. Okay. So, this will represent the reinforcements. Okay. So, similarly we can make the top reinforcement, and here again at the bottom we can create nodes like this, join the nodes with the lines, okay, mesh them using the beam elements. Okay. So, this creates the bottom reinforcements. Okay. So, this way we can create the geometry of the concrete, and this way we can create the geometry of the beam, we can create the geometry of the reinforcements. Okay. So, at the end of the day what we are getting is a reinforced concrete beam with concrete as the solid elements and the bars as the beam elements. Okay. After we have created the elements, what we can do is that we can choose the nodes of the beam. Okay. So, here is the beam, we can choose this nodes, okay, like this, okay, and we can give the boundary conditions. Okay. So, here we have restrained it in the x direction, we have restrained it in the y direction, and we have restrained it in the z direction. Okay. It means that this cannot translate longitudinally this way as well as the vertical way. But here if you look closely, here we have kept Rx, Ry and Rz as open. Okay, we have not restrained it. Okay, so it means that it can rotate also. Okay, so the translations are not allowed, but the rotations are allowed. Okay, so depending upon the given problem, you can choose any of the thing as restrained or unrestrained. To restrain it, we have to switch it on, and to leave it open, just put nothing here. Okay, so this way we can give the boundary conditions to the whatever model we are creating. Okay, so single point constraints, these are called the single point constraint. This gives the pointwise constraint. Okay, and it constrains nodes in the translation or the rotational degrees of freedom. So x, y, z are the translation degrees of freedom, and Rx, Ry, Rz denotes the rotational degrees of freedom. Okay. Okay. So after we have created the geometry, after we have created the boundary conditions, we can give the sectional properties. Okay. So for the concrete beam, we can give the solid properties. Okay. For the reinforcement, we can give the beam properties. Okay. So this is the keyword manager. So from there we need to choose the section, and from the sections for this particular problem, we will be using two types of sectional properties: solid for the concrete part, okay, and beam for the reinforcement part. Okay. So if we switch on solid, okay, we need to give some name. So we'll just give it solid. You can give any other name, x, y, z, or any other name you wish. You can give concrete solid also. Okay. So section ID will be automatically 1. Only thing is that you need to take care of this EL form, elemental formulation. Okay. So if we look at the bottom, okay, there will be different elemental formulations coming out here. Okay. So you can just choose the default one, which is the solid element. Okay. So or any other elemental formulations that are keeping here. Okay. So these are the only two cards required. Okay. Okay. And after that, push done, and this thing is done. Okay. So the concrete element part is done. Similarly, for the rebar part, you have to give a name out here. We can give rebar, solid rebar, steel rebar, or whatever is there. Okay. Then the section ID will be, here we use section ID 1. Now it will jump one more space, so it will be section ID 2. Again, the thing that needs to be taken care is the EL. Okay. So element formulation. Okay. So depending upon the whatever element formulation we have to use, you put that element formulation. Okay. And after that, we can give the cross sectional properties also. Okay. So this way we can make the solid elements and we can make the beam elements. Okay. So we have created the geometry, we have given the boundary conditions, and we have created the sectional properties. Okay. So after creating this thing, we give the material properties. Okay. So for we are modeling it as a reinforced concrete elements. Okay. So we need one model for the concrete, we need one model for the steel. Okay. So for the concrete we are choosing as CSCM model. Okay. So there is a CSCM model, conventional concrete model is present. Okay. And there are other type of concrete models also present. Okay. So depending upon the usage, you can choose any of the concrete models. Okay. Similarly, for steel formulation, we are using the plastic kinematic elemental formulation. Okay. So again, there are other models present. So depending upon the usage, any type of appropriate model can be chosen. Okay. So this is the CSCM model, and this is the steel model. Okay. We will talk about the erosion model just now. Okay. So let us look into the concrete model. Concrete model, again, name, we can give any name. Material ID, we can give it as 1. RO is the density of the element. Okay. So since this is concrete, we are giving it as 2425. Okay. Normally we give 2400 to 2500. Okay. So any number in between, we can keep this here. Okay. There is an erosion criteria. Okay. So we will talk about this erosion criteria now. Okay. After that, we have to give the FPC. FPC is nothing but our FC prime. Okay. So this is the FC prime, which is different than FCK. Okay. So this is FC prime. Okay. The strength of the concrete. Okay. And this is not FCK. So whichever we are using, okay, we have to take our FCK value and convert into the appropriate FC prime value. Okay. So this thing we need to take care. Okay. Similarly, for the steel we can give any name, steel bar, steel rebar. Material ID, again for the first one we used 1, here we will be using 2. RO is the density, so steel density is 7850 that we are using. E is the modulus of elasticity of the steel. PR is the Poisson's ratio of the steel. Sigma y, this is sigma y, okay. Sigma y is 415 to 500 or 550, okay. And these are the values that we are using, okay. One important factor to consider here is erode, that is the erosion criteria of the concrete. What does it mean? It means that when it attains 10% strain, okay. So here you see it is 1.1, it means that when the strain is more than 10%, the element will be deleted out there, okay. And this is again an erosion card, okay. So using any of these values, okay, we can also give at what value our the solid section will be deleted or it will be eroded, okay. So maximum strain, here it is also given as 0.1, okay. So these are the erosion criteria or the deletion criteria that are used for the deletion of the concrete and the steel. So same thing can be used for concrete, okay, and similarly the erosion criteria can be used for the steel also, okay. So this is the erosion criteria for the concrete, this is the erosion criteria for the steel, okay. It means that when the strain becomes more than a specific value, the element will be deleted either in the concrete or in the steel, the way we are using it, okay. So after that we have defined the materials, we have defined the sections, now we need to assign it, okay. So we need to assign the part ID, section ID and the material ID, okay, to the beam, and similarly we need to assign it to the reinforcement also, okay. We need to tell the software that the solid that we created, okay, has a section ID, the section ID that we defined earlier. Remember we were defining the section ID, okay. Here we defined the section ID and we are making this for the solid beam, okay. So here it is given to the solid beam. Similarly the material ID, okay, we created a material ID 1 and this was for the concrete, okay. So then you will tell the software that this is for the concrete. Similarly for the rebar, this is the part ID for the rebar. The section ID, we created section ID 2 for the rebar, okay, we created section ID 2 for the rebar, and after that we created the material ID 2 for the rebar, okay. So here we will tell the software that the section ID 2 and material ID 2 is for the rebar, and here we will tell the software that section ID 1 and material ID 1 is for the concrete part, okay. Now our sections are ready. Now we need to apply the loading, okay. So we are applying the loading using the keywords blast enhanced and blast segment set, okay. So in the blast enhanced what happens, okay. So we will give one ID, okay, M, this is the mass of the charge, okay. So this is nothing but kg TNT, okay. So here we are putting 100, so we are putting 100 kg of TNT, okay. So this is basically our Q value, okay. And then we have XBO, YBO and ZBO, okay. So this tells the location of our charge, okay. So 100 is the 100 kg TNT above the beam, okay, and this is at location vertical direction 1 unit, okay. So this is 1 and it is location at x, in x direction, y direction, it is located at the center, okay, and it is 1 unit, okay. So this specifies the location of the charge, okay. Now there is one more additional card used with this charge, okay. This is the blast surface, okay. So in where we want to apply the charge, we want to apply the charge in this face, this face, this face, okay. So whichever face we want to apply the charge, we will choose that node, okay, and make this thing as a segment, okay. So it means that the blast having a magnitude of 100 kg of TNT located at 1 unit from the center, okay, is applied on this particular face. So this particular face, whichever face it is being applied, it is being given by this segment, and the magnitude and the location is given by this card, okay. So in this way we apply the blast loading, okay. So after the loading, remember we modeled it using a RCC beam, okay. While modeling, okay, we just made the sections. Okay, we made one concrete section and we kept the rebars here. Okay, we did not tell what is the interaction between these two. Okay, so here we now need to tell the software what is the interaction between the two. So we are putting the constraint property. Okay, we are telling that it will behave as a constrained Lagrangian solid. Okay, basically it means that whatever the concrete, whatever the way the concrete is going to bend, okay, or it is going to deform, the rebar will mimic that property. Okay, it simply means that the nodes are constrained, nodes of both the bar and the concrete are constrained. So this is a very beautiful step that is used in LS-DYNA. In other software, what will happen is that we need to take care of the nodes of the solid body as well as for the beam. They need to be put together. Okay, but in LS-DYNA that is not the requirement. What we need to do is that we can give the constraint criteria and both will mimic the deformation of each other. Okay, so this is a very powerful tool that is present in the LS-DYNA. Okay, and we are putting it as a Lagrangian in solid. Okay, and then we give the control cards. Basically we are telling the software to run for what times. Okay, so we are asking it to run for 5 seconds. So this is the second. Okay, and whatever are the outputs that we require. Okay, and at what interval the outputs are required. So we require the outputs at every 1 second. So we are putting it as 0.1. Okay, and then we run the LS-DYNA file. So we run the LS-DYNA file, and after running we open the D3 plot file, that is the output files. Okay, so before we go into the post processing, one more good thing about LS-DYNA is that it is unit independent. Okay, so till now whatever we have seen, okay, from the starting, okay, so there are no units anywhere. Okay, you only see that these are all pure numbers. Okay, there is no unit in LS-DYNA. Okay, so whatever numbers we are putting, we have to put it by ourselves, choosing a consistent unit. Okay, let us say if I am choosing a unit as kg for mass, meter for length and second for time t. Okay, so this is my chosen units. Okay, after that whatever values I am putting, let us say I am putting density. So density will be kg per cubic meter. Okay, so it will take the values in this parent unit also only. Okay, so remember we put the density as 2450. Okay, it means that my base unit I choose as kg meter and seconds. Okay, and that's why I am putting 2450. Okay, similarly for E. Okay, this is 2.1 E11. Okay, or 210 GPa. Okay, so this comes from my choice of my base units. Okay, if you look into the runtime also, okay, I am using 5. It means that I have chosen 5 seconds. Okay, similarly I can choose any other units also. I can choose milliliters, or no, not milliliters. I can choose time as milliseconds. Okay, length as millimeters, and mass as grams. Okay, so what will happen is that after that all the other values, the density, modulus of elasticity, okay, everything I will have to put in this units only. Okay, so LS-DYNA, in LS-DYNA we can choose any units, we can adopt anything, but we need to be consistent when we are putting the derived units. Okay, so after that we run the simulation and we got the behavior of the system. Okay, so similarly you can model the system and you can run any model and check and verify, and you can verify with any experimental results to get the validation of the system, and after that you can use this for running your own simulations. Okay, so again this is the step by step of creating the frame sections, and after that we are applying the boundary conditions for the frame sections. Okay, we are giving the sectional properties. Okay, similarly what we did earlier. Okay, we are giving the material properties. Okay, after that we are giving the part properties. So basically whatever sections and with whatever material properties we created, we are telling it that it goes for this particular part. Okay, after that we are applying the loading in the section. So, here we are defining the blast loading, and here we are defining where the blast loading will be applied. Okay. After that, the control card, we tell the software to run for 10 seconds. Okay. And what are the outputs that we require and the interval at which I need those outputs. Okay. So, at every 0.1 seconds I need the outputs. Okay. After that, we run the simulation and we open the D3 plot file, and here you can see the simulation at various instances. Okay. So, this way you can model beams, columns, frames or any other system, validate with any experimental or any other database, and then can perform your own simulations. Okay. So, this is an LS-DYNA practice problem. So, here the length is given, section properties is given, the blast parameters are given, the material properties are given, okay, and the boundary conditions are given. Okay. So, this thing we can model in LS-DYNA. So, this is the step by step, okay, procedure of how to model in the LS-DYNA. Okay. And so, this is the consistent units that I was telling. Okay. So, we can use units as kg, meters, seconds, then our force is in Newton, pascals, energy in the joules, and these are the sum of the values. Okay. Similarly, we can use any combination of the units. Okay. Only thing is that whatever base units we choose, okay, we have to keep in mind the equivalent derived units. Okay. So, they has to be consistent. Okay. So, this is the table which you can use if you are using any other units. Okay. So, this is how the value should be given. Okay. So, just for a recap, we introduced the general considerations for the extreme events, we gave the quasi-static approximation principles, we talked about the elementary impact mechanics, we talked about the stress wave propagation and interactions, and we talked about the energy absorbing systems and their characteristics. Okay. We also dealt with the structural elements under impact load, we dealt with the dynamic properties of ductile materials under high strain rates, we dealt with the blast effects and the design requirements. Okay. We saw the loading on the structure caused by external air blast. Then this was broken down into two parts. Okay. And after that, we looked into the pressure impulse diagrams and their applications. We did examples on the dynamic response using single degree of freedom system analysis, and after that we looked into the analysis and design of the structural elements under blast loadings. We looked into the failure mechanism of the structural elements under extreme loadings. Okay. We looked into the dynamic buckling phenomena in structures. We looked into the 2 degree of freedom system analysis. We looked into the multiple degree of freedom analysis methods for the structural elements subject to impact. We looked into the multiple degree of freedom analysis method for the structural elements subject to blast loadings. We looked into the finite element simulation modeling, and we did examples on design of the elements. Okay. So, this way we tried to summarize the extreme and vast subject of the blast and impact loadings. So, this was just small recap. Okay. What we tried to achieve in the course is very vast, and we tried to achieve some of the topics that are relevant for the design and analysis process. You can use this course as a design aid to learn and again improve in the courses. The course is very vast, and these are just some of the tools that we provided so that you can go in the real life and explore the course. Thank you. Please practice the problems. Thank you for the help.